some things that are just added to the web page now, which I want to point out. So you will remember that there is a, no, before I forget, cool. Okay. All right. Well, there will appear on the web page within a few minutes of once I get back up to my office some links to some PDFs and tech files. These PDFs and tech files will be related to the final project. So the idea I'm going to give for the final project, you don't have to follow one of these if you would rather do something else, is I'll propose here are some interesting results to think about. For instance, in analysis 1, we don't hit the notion of the derivative. Not because it's hard, just because, well, in fact, because you can do a lot of things really easily, so easily, in fact, that like you can just do it. One of the final projects is define the derivative, prove some things about the derivative, like the mean value theorem. Also, known as the most valuable theorem in some circles. It's an important theorem. That you all remember from Calc 1. And go so far as, say, L'Hopital's rule. And so I'll post some guided proofs for things like that. One of them is, well, what's another approach to lim soup, which hands you a proof of the Bolzano-Weierstrass theorem midway through? It just gives you both things all at once. That's one of the final projects that I'll propose. There's an interesting property of series that we didn't hit called the rearrangement principle, the Riemann's rearrangement principle, which says that if you have an absolutely convergent series and you shuffle the terms around, so you add up all the same numbers but in a different order, you should get the same result, which seems intuitively obvious, right? Addition should be. If you have a conditionally convergent series, that's not true. You can add up the terms of that in different ways and get different answers just by listing them in a different order. So that's one of the final projects that I'll have you go through. My intent was to have these links actually working, but then I realized I had an obligation before this, and so I put some things up, didn't test if I put the links up correctly. Cool. So, I know there's not a whole lot to go on right now. People have any questions about final project kind of things? Yeah. You want to collaborate on it and like prove each other's stuff. You want to talk about the point together, but I want your own way. In fact, I strongly encourage you to prove each other's things. Like, the more eyes that are looking at these things and making sure they look good, the less you have to wait for me to get around to finding time to give feedback. Yeah. The day of the final exam, which is on campus, but I believe it's the Friday of the final exam.
Sorry, did you know the time?
No, it's on campus. Okay. Even if I told you, don't trust me at all. It could be Monday for all I know. I think it's Friday. Go to campus and check it out. Sometime on the final exam week, if it's like Friday.
Oh, it's due on Friday. Okay.
Well, is the final exam on actually Friday? Are you positive? Okay. Okay, cool. You remember what time on Friday? No. Okay, cool. Neither do I.
I'll have it in a second.
Okay. It doesn't matter a whole lot right now, but I guess we're on the topic, so you may as well know now. So I'll have an extra couple office hours during that final exam week, during which time you'll get to come by my office and, well, really, I'll put up a place for you to put submissions for drafts of the final project, which I'll give feedback on, and then you'll correct, and then I'll give you more feedback on, and then you'll correct again. There'll be a few iterations of that. My intent is that the final project be typeset at least. ideally LaTeX, and I'm going to set up the final project to be easy to tech, in that I'll give you a tech file to start with, which will have things like POM statements and references. Yeah.
Friday 8 to 9:50.
Friday 8 to 9:50 a.m. I assume.
Yes.
Okay. I don't know if there's a 9 to 10 time slot in the night. I guess it would be weird if no more. Especially the Friday.
Yeah.
Cool. The other thing is, did I not get that up either? I'd intended to have a link to the macro treat on the webpage that I could point to now. But I've sent out the link to the macro treat schedule. Everyone's planning on coming to some talks, and in particular, not coming to this class on Monday. In fact, what was this 3 times? 3:08. There will be a talk here during this hour, I believe. Yeah.
And you would like us to come talk to you in office hours at some point and explain one of the talks?
Yeah, I think that'd be a nice thing to do. I guess if you're the type of person who would really rather do a written summary, I wouldn't like that as much, but if you really want to do that instead, that's an option.
Mm-hmm.
Cool. Yeah.
And do you know your availability for office hours, later on in the day? Or?
Let's say right after our class today is a good time to talk.
Okay.
Cool. All right, let's get started. So, when last we talked, we were in the midst of the proof of the intermediate value theorem. And here was the mindset. So our goal was solve f of x equal to c Gesundheit. Find a solution to that equation given this information. And we came up with a candidate. C equals the supremum of the set of all x in A, B, such that f of x is less than or equal to m. There's a set whose supremum should solve it just intuitively. The last place where f of x is less than or equal to m should be a place where f of x is equal to m on this. As you go past it a little bit, it's suddenly figure that out. So now all we have to do is make that concrete. Let's do that. And I guess that's the set that we called U right here. So let's... Yeah, the dot cam's supposed to be on. So that set up there is the set that's called U right here. And what do we have so far? We have that the supremum actually exists. We need the supremum to actually be in the domain of the functions. Let's start with that. So let's verify that C is in the interval from A to B. So we want A less than or equal to C, which is a supremum, is less than or equal to B. Nice. So remember, C is the least upper bound on a set. So if we find any upper bound on that set, that other upper bound will be bigger than. And this set's definitely contained in AB, so what's an obvious upper bound on this set?
B.
B. Let's use that. Why is C in AB? We've already seen that B is an upper bound on U. Yep. Since C equals the supremum of S is the least upper bound, what can we conclude? Okay. B is an upper bound and C is the least upper bound, then we can conclude what inequality? Yeah.
C must be less than or equal to B.
Yeah. But any upper bound is bigger than the least upper bound. We know that A is in U. By assumption, f of A is less than or equal to 1. That satisfies the defining property of what it means to be in the set big U. A is in U, and C is an upper bound. So what can you conclude? Yeah. Oh, hey, is that exactly what we need?
Hey, what are you doing there?
So C is in the interval. Groovy. Now let's actually verify that f of c is equal to m. And we'll do it in 2 steps. First, we'll check that f of c is less than or equal to m. And I'll take the mindset that I want to give myself some flexibility. I'm going to add an epsilon and then prove that inequality for every positive epsilon. So here's what I'll really prove. I'll prove that f of c is less than m plus epsilon for every epsilon bigger than 0. Then you can imagine taking a limit. What's the limit of m plus epsilon as epsilon goes to 0?
M?
What's the limit of f of c as epsilon goes to 0? F of c, right?
Oh.
There's no epsilon? Oh, that means you should have an inequality as a consequence. So that's what I'll actually prove. So let's do this. We know the function is continuous. So it's continuous at c. We'll pick this epsilon bigger than 0. Since f is continuous at c, there exists some delta bigger than 0 so that, what's the definition of continuity?
For all epsilon greater than 0,
Mm-hmm.
there exists a delta greater than 0,
Mm-hmm.
such that if 0 is less than the absolute value of x minus p being your point, x being the value you want, less than delta, then the absolute value of f of x minus f of p is less than epsilon.
Nice. Let's just change some of the names of variables.
Yeah.
Is p the place where I want to check for continuity?
Yes.
No.
Oh.
C.
Oh.
F is continuous at c.
Specifically speaking, no.
Right, so you gave me the definition, but not in the particular context I want. And there's one other error that I'll point out. It's not so, well, it is an error. It doesn't make the statement wrong, though. The 0 is less than is not necessary. That's for limits, not continuity.
Oh.
And maybe I'll give myself some flexibility here as well. I could put any positive number there, right? So who knows if I'll want an epsilon there at the end. I can put any positive number there. I'll figure out what focal epsilon I want that to really be. People happy so far? Yeah, I guess we do need that. And not x and u. What's the domain of this function?
A to B.
Yeah. Nice. All right. So let's hold on to this quantity delta. Now let's take advantage of the fact that C is the supremum of a set. We have a reformulation of the supremum that takes a positive number as an argument. And let's just draw a picture of it for us. So if there's C, that's the supremum, C minus delta. Could C minus delta be an upper bound on this set? No. So there has to be a thing in there. There exists some x in u such that C minus, and I can put any positive number I want here. So is the purple actually different from blue? Not really. For emphasis, I'll underline it. I might change it later. And it's less than or equal to C because C is the supremum. Cool. So, does it follow then that absolute value of x minus c is less than delta? Yeah. Should we go through the walk of checking it, or is that obvious? Should we go through it? It is obvious. Let's go through it. So let's maybe even just try to do it directly. Absolute value of x minus c. Well, I know x is less than or equal to c, so is x minus c positive or negative? So this absolute value is either the same as x minus c or it's the same as c minus x?
Yeah.
Which one, though? C minus x, because c is at least as big as x? Cool. And I know that x is bigger than c minus delta?
Yes.
So that means that C minus X, this thing, is bigger than C minus delta. So far so good? Oh, well, what's C minus delta?
Negative delta.
Well, I think it's positive delta. Double negative.
Oh, yeah.
And I guess this is true since C minus delta is less than X. Thus, absolute value of X minus C is less than delta. Now let's appeal to 7.10. So I know that the absolute value of X minus C is less than delta, and I have this if-then statement. So what conclusion can I make because of that? Yeah.
I'm sorry, can we just jump back there? Would it be easier just to say, like, okay, we know that, so we subtract the C over, and we have negative delta is less than X minus C, and we just take the absolute value of everything?
Cool. Yeah, that would do too.
Okay.
Well, no more way to do a thing. I'd buy that.
All right, just want to make sure that was like a logical sound.
Yeah, I think so. Either way, though, what does 7.10 now tell us? Which is underlined in red midway up the display. We have an if-then.
So, does it imply that f of x minus f of c, the absolute value of x, is less than f1?
Cool. All right. So there's something that's good. And let me tell you why it's good. I want to get control over f of c. I know something about f of x. What set does f of x live in by assumption? What set does x live in by assumption?
The set that we do.
Yeah, but there's a smaller set that lives in. No, I'm not going to do that. X is in here. I'm going to step on this and tell you.
Oh, yeah.
So the set X is in the set U. The set U is f inverse of negative infinity to m. So what can I conclude about f of x?
Would be f would just be negative infinity now.
Mm-hmm. Right? Cool. So what inequality does that buy us?
Let's see.
X, absolute value of x minus c, no?
Nice.
Oh.
And let's put this together. This plus this. So right now, what do we know? We know that there's m. We know that f of x is less than it. I know that f of c is within an epsilon neighborhood of f of x. So f of c is somewhere in there. Does it follow from that that f of c itself has to be less than m? No, it could be like in this space, right? Does it follow though that it's less than m plus epsilon?
Yes.
Yeah, cool. I think that does it then. Let's just make that conclusion. Let's use this and this to deduce that f of c is less than m plus epsilon.
What is the arrow that that was on everything?
Which arrow? This one?
No. One for the now.
I want you to point, so in context nothing, but right now, I want you to think about this inequality and that inequality, and tell me why this inequality should be true.
Oh.
So I guess we'll start with this. Since that inequality, could you solve that inequality for f of c?
Yeah.
I think so. It wouldn't even take much effort. Like you could possibly even deduce what it should be without doing the work. F of c should be between x minus epsilon, f of x minus epsilon, and f of x plus epsilon.
Yeah.
Our notes is the fact that we know something about f of x is less than m. Let's see, so I know that f of c is less than or equal to f of x plus epsilon, strictly less than f of x plus epsilon. And I know that f of x is less than or equal to m, so what can I get out of this?
Sorry, probably right.
So, this is just this line right here. I also know f of x is less than m, so what can I conclude? Less than or equal to m. Yeah, great. Oh, hey, let's go back to the beginning of this. I said I would prove that f of c is less than m plus epsilon for every epsilon bigger than 0. Somewhere in there, did I declare epsilon universally as any positive number? Great. So that means for absolutely any epsilon, all that stuff I did holds. And I get this conclusion out. Feeling pretty good? Nice. And now, since we have f of c is less than m plus epsilon for every epsilon bigger than 0, you can take the limit as epsilon goes to 0 if you like, or you can appeal to a theorem that we proved really early on in the semester to deduce a loose inequality. If f of c is less than m plus epsilon for every epsilon bigger than 0, what can you conclude?
F of c is less than m.
Or equal to. Or equal to.
Oh.
Groovy. So there's half the proof. You want to show f of c is equal to m? How do you do that? Well, you show that it's at least as big as m. Then you show it's at most as big as m. In order to show it's at most as big as m, you really just show that it's not much bigger than m. It is less than m plus epsilon. Now we'll go the other way. We'll show that it's not much smaller than m. All right, let's do it. Next claim, f of c is bigger than or equal to m. And so how am I going to do this? Let's draw a picture of the proof. There's A, there's B, there's this quantity C. If I take an x that's just a little bit bigger than C, could that x possibly be in the set big U?
Yeah. Isn't set u maybe, right?
No.
Oh.
The set U was right.
Oh, okay.
So this x is not in U. So if that set x is not in this set, what can you tell me about f of x?
Oh.
not in this set? Because
Oh,
U is
yeah.
here. So what inequality can we conclude?
F of x would be greater than f of c?
Not greater than c, but greater than n.
Okay.
So here's this value, f of c. I would like f of c to be at least as big as n. I've just checked that f of x is bigger than n. Is that f of x value, can I make that as close to c as I want? Yeah, so I think I can get like little epsilon bars there. And that epsilon can be as small as I want as long as I choose the x value correctly. So I think the other half of the proof will look pretty similar. Let's do it. Though I guess there's like one shortcoming. What if c were b? Could I do that? Go through this argument if c were equal to b?
No.
No, there's nothing in the domain to check. But what do I already know about f of b? By assumption, basically.
So it's the f bound?
That is a little bit bigger than n. So if it is b, then you are already done. So let's just say that. If c equals b, then by assumption, f of c is equal to f of b is bigger than or equal to m. Only need to say by assumption once. So we're done if c is equal to b. So I may as well deal with the case that c is not equal to b. It's strictly less than b. Just as before, instead of proving the thing on the nose, I'll prove that f of c is less than m plus epsilon for every positive number epsilon. People feel good so far? So, first things first, we can appeal to continuity in the exact same way. This function is continuous at c. So that means for any epsilon bigger than 0, there exists a delta bigger than 0, so that what happens?
For all x in your domain, there exists a delta greater than 0, no.
And the delta comes before the x,
Yeah.
so it wouldn't go there anyway.
Such that if we have our absolute value of x minus c in this case is less than delta, then we have f of x minus x to f of x is less than epsilon.
Yeah. Groovy. And the domain is AB. So here is what I'll do. Let's go ahead and take c to x to be c plus a small number. That small number will be the min of delta over 2 and b minus c over 2. And let me tell you the job of each of those things. That delta over 2, that probably means that x is within a distance of delta of c. So there are two things in this min. I should explain to you why both of those things are there.
Okay.
So the reason for that, well, that's just to make sure that x is actually really, really close to c, within a distance delta of c. And let's do that. Well, I guess we also need that c to be less than x. Is it obvious that c is less than x given that?
Yeah.
Yeah. Because both of the things in those parentheses are positive?
Yeah.
As delta over 2 is positive, and b minus c over 2 is positive, c plus the min of delta over 2 comma b minus c over 2 is bigger than c plus 0, which is c. C is not is the supremum of U. So could that thing, if it's bigger than C, possibly be in the set big U? No, the supremum's an upper bound. This quantity x is bigger than C, so as
x is, as C is, an upper bound on U, x cannot be in U.
Feeling pretty good?
So, what else do we have? I have that x is not in U. So x is not in f inverse of negative infinity, comma, m.
So, by the definition of the preimage, I guess one of two things could happen.
Yeah.
And one of them is the obvious thing. Either f of x is not in negative infinity, comma, m.
Right, by the definition of what the preimage means. Or maybe x is accidentally not even in the domain. And if you're not in the domain, you're not in the preimage. So I guess I should convince you that this x is actually in the domain of the function.
And that is where this comes in.
Let's argue that x is strictly less than b.
Well, all right, so let's try to do it. So I know what this x is. X is equal to c plus the minimum of delta over 2 and b minus c over 2, with that underlined.
Let's see. C plus the min of two things. The min of two things is automatically less than or equal to either of those two things.
Yeah.
All right. So what is x less than or equal to?
Should be C plus C over 2.
Yeah, and that's the same as the average.
Yeah.
If you add half of the difference to something, you get the average. Is that less than b? Yeah, because c is less than b.
So x is less than b.
I want x to be in the interval from a to b, though. So why should x be at least as big as a?
Is that because x is equal to c plus the minimum of the two things? Which is it because also then we know that c is between a and b?
And in particular, it's bigger than a.
Yeah.
So this is going to be bigger than or equal to a, because c is bigger than a, plus 0.
Feeling pretty good?
Thus, x is in a, b. And maybe I'll add a conclusion right here. So, by 7.12,
Let's see what we can do. So go back to 7.12. Either this is true or that is true. Is one of those two or statements now known to be false? So what can you conclude?
Wait, both of the or statements or one of them?
One of them is known to be false.
Okay, so then the other one either has to be true or false.
It just has to be true.
Oh, wait, because wait, why does it have to be true?
Today is Friday, or I am a duck. I am not a duck. Therefore, today is Friday?
Okay.
When someone tells you one or two things is true, and then tells you that one's false, you're just told you that one's true.
Oh, so we know that one of them has to be true.
Yep.
Okay, all right, cool.
If it's Thursday, then I am still not a duck. I guess that statement I made is only true on Fridays.
Okay.
But it's the only thing I can come up with on short notice. So, by 7.1.2, f of x is not in negative infinity to m.
All right, so that gets me to the point on the board of knowing that f of x is bigger than m. Now let's explain why f of x is close to f of c.
And let's do it by explaining why absolute value of x minus c is less than delta. So let's just do it by writing it out. I have an explicit definition of x. Let's use it. C plus the min of delta over 2 b minus c over 2 minus c, all that in absolute value.
And that's just by using the definition of x. So you look at this thing in the absolute value, what does it all simplify to?
Oh, we just have a minimum.
Let me just have the minimum. Is it a minimum of two positive things? So can I write the absolute values? All right. And I just need it to be less than delta. Why is that less than delta? Yeah.
Because it's less than or equal to delta thing, and one of the things is half of delta.
Nice.
So this is literally equal to the min of delta over 2 b minus c over 2 less than or equal to delta over 2, which is less than delta.
So why was the delta over 2 there? The delta over 2 was there to make this happen. We feel pretty good?
All right, so we now have the absolute value of x minus c is less than delta.
We chose this delta for a reason. We chose it by appealing to continuity. So look back to the place where we used continuity. I know that the absolute value of x minus c is less than delta. So this is inequality 7.11, currently at the top of the projector screen. What can I conclude? Yeah.
The absolute value of x minus f of c is less than epsilon.
Nice, nice.
Is this now starting to feel pretty familiar from what we did to get the opposite inequality?
Possibly. I'll be honest, I wasn't tracking very well.
So right now I know f of x is not in the interval from negative infinity to m. So let's start with that. I think that was supposed to go up here, but it didn't make it there. So let's see, as f of x is not in negative infinity to m, I can make a conclusion, right?
Since f of x is not in the interval from negative infinity to m, f of x is not less than or equal to m?
Yes.
So it has to be greater than.
Thus, let's go ahead and label this as star. Let's combine this with star. I know that f of c is bigger than or equal to f of x minus epsilon.
Bigger than.
F of x minus epsilon. Though maybe I'll ask if people are okay with that. Is it clear why, how star implies the thing that I wrote?
Yeah.
Same way we did it on the last page. So I didn't even really do it on the last page, right? You would erase the absolute value by putting a minus epsilon and plus epsilon on either side, and then you would add f of x to both sides.
Yeah.
Perfect.
All right, so let's now put this together. That is known to be bigger than m minus epsilon. Do we now know that f of c is bigger than m minus epsilon?
Yes.
Do we know that for absolutely every epsilon bigger than 0?
Yes.
So what can we conclude?
It is bigger than
Or equal to. In fact, it better be, or the or equal to option better be there, because I want to conclude that it is equal to.
Oh, okay, good. Is that like, we could say that it's strictly greater than, but we choose to sort of loosen the inequality so we can get the thing next to it?
No, it's more than that. If you put a strictly bigger than here, that would be a false conclusion. And let me explain why. Is 0 bigger than 0 minus epsilon for every epsilon bigger than 0?
No. Wait, you say greater than equal to or just greater than? No. Oh.
That is true, right? Epsilon is positive.
Oh, greater than 0. Never mind, yeah.
So this is true. In fact, if I put it bigger than that would still be true. It would not be even, it would be just as true. Is that true?
No.
Is that true?
Yeah.
Yeah, so you need that whole equal to that one.
Okay.
Even though you prove a strict inequality for an arbitrary positive number, you still only get a use one. I feel like that's the same logic, like you prove that like limits interact well with inequalities, but only with less than or equal to, not strictly less than.
Okay.
Same logic. Good. People feeling good? Does this seem like the proof is basically done?
Mostly.
Let's wrap it up. Since we have proven that f of c is bigger than or equal to m, and f of c is less than or equal to m, does it follow that f of c is equal to m?
Yes.
Oh, is that all we wanted?
Yes.
I guess it better be, because there's a little Helmholtz box there saying that the proof's done. Groovy. So, there's another proof of the IVT. We're not going to cover it. In fact, maybe I'll give you this hint. As written, there is something that is wrong with the proof. I noticed while I was looking at it, it was a good thing that people didn't choose this one. Otherwise, I would have, said some false things. There's something wrong in the notes in this section. So here's a fun bonus exercise. Find the error. There is one. And maybe I'll even tell you that something in that proposition is false. I'm not necessarily needing you to find like an explicit counterexample, but tell me what secret added assumption I've made, or something that's not justified in the argument. Nice. So I think with 5 minutes remaining, the next thing theoretically on the schedule for today is introducing uniform continuity. I think with 5 minutes to go, well, maybe I'll give you a feel for what uniform continuity is supposed to do.
So let's start down the definition of continuity. So what does it mean to say a function is continuous?
So you can draw the line without picking up the pencil?
The right definition. The epsilon delta.
What is that? And then there exists a delta greater than 0, such that if 0, wait, no, we dropped 0, that's what it is. If the absolute value of x minus your point of interest
Yeah, I guess I can repeat.
is less than delta, then the absolute value of f of x minus the function of the point of interest is less than epsilon.
Yes. And I'll add, right, for every point of interest. Well, no, but that's on me, right? When you gave me what I wanted.
Okay, all right.
And maybe I'll also put this.
Okay.
And let's just think about how you would then start writing down a proof that a thing is continuous. You would say consider any p in u. You would then consider any epsilon bigger than 0. You would then need to come up with a choice of delta. I guess those two are in the opposite order of these two, but does it matter which order you declare universal things in?
I don't think so.
No, either way, you're considering an arbitrary one of them. You'll say let delta equals, and then you'll write something down. What things is that delta allowed to depend on?
Epsilon and P.
Epsilon and P. Anything that comes before it. So here's the idea of uniform continuity. So this means that like each delta depends on the choice of epsilon and depends on the choice of P. A function is called uniformly continuous if you can pick a single choice of delta that walks at absolutely every P. So a function is uniformly continuous if this delta doesn't depend on P anymore. How would you change the definition to get that to happen? Yeah.
You just change the P for epsilon. For all epsilon. Or just get rid of that the other one.
Well, you still need, like, there still is this P. That's going to be there.
Maybe for some.
And we are going to move this somewhere else. So how could you tell that delta depended on P and epsilon?
Because we were considering any epsilon and P. So.
And you say those already because those appear in the definition. So what would happen if I just took this for all P and moved it after there exists a delta? What if I took this and I put it here? Then would the delta be allowed to depend on P?
No.
There's the idea of uniform continuity. The function is uniformly continuous. If for every epsilon bigger than 0, there exists a delta bigger than 0, such that for all P in U and for all x in U, if this, then that. And that seems like a really minor difference. But it really makes a big difference in how well behaved the function will be.
I mean, that would be like uniform continuities have a subgroup of all continuities.
Yep. Uniform continuity implies continuity, because you just have less freedom in how you choose your delta.
So is that like an all thumbs are fingers argument, but not all fingers are thumbs type situation?
Yeah, sure.
Well,
And, right, kind of like that. Thumbs can do some things that fingers can't. There are some results that don't work with just continuous functions. There's a limit you could try to take. You have a function of two variables. Under what circumstances is this the same as the limit as y goes to b, and then as x goes to c of f of xy?
In that case, if it was uniform, they would be equal, but if they're not uniform, then they're different, so they would be different.
Yeah. So there's an interesting fact. If you just have continuous functions, this can fail.
oh.
If you have, was it what, uniform continuity you mentioned there?
I don't know.
I think probably differentiabilities, which implies uniform continuity. In a neighborhood, uniform continuity in a neighborhood. You can pull this off.
Okay.
And so this is something that we'll do some starting next time.
Okay.
Cool. So, at that time, look to the webpage for the following things. I'm going to put the schedule for the master tweet up, even though you already have it, but it's in an email, and I know that emails get buried. You probably have it in several emails, but that just makes them more buried. Yeah?
For test retakes, would you like this midterm back?
Yeah, scan it in. Itwill be electronic, just like the other one.
Okay, so we're essentially going to do our corrections.
Yeah, right.
As such, like we did before, piece of paper, rewrite what we did, start it in.
Yep.
Okay.
Yep, using, so I'd scan in both your commented up one and the other one so I can know what I have to grade.
Okay. Open notes.
Say again?
Open notes.
Yeah, you can read anything now.
Okay.
Have a good day.
You do?
And are we still doing the average score of the two?
Yes, sir.
Okay. Only up to 90%?
Only up to 90%.
Okay.
Which doesn't matter if you score less than 80%. I don't remember what you got, but.
I scored like 75.
Okay, so it'll just be the average.
Yeah. So I can get like an 88 out of it, I think, somewhere in there.
Yeah.
That'll be good.
Oh, it's for the thing that about when you do Villa Frost hours on Monday. I'm not like super
Oh,
concerned.
yeah.
I'm pretty flexible, but I was curious if you
Oh,
knew.
on Monday.
Oh, just like for the not for the day,